Gym class just ended. We've got 20 basketballs that we've got to put back into these 4 bins. We're assuming all the balls are identical to each other. So how many ways can we do that? Well, one way is maybe put 5 balls in each bin. Another way might be to put 14 balls in the first bin and 6 balls in the second bin. So what's the math that's going to help us count all the different ways we could do this? We need what's called the binomial coefficient. Read this as n choose k. And it's how many ways you could pick k out of n things if the order doesn't matter. Most scientific calculators got a button for that, and the next trick we're going to use is a technique that's called stars and bars. We'll let the 20 balls be represented by 20 stars, and we'll use 3 bars to visualize the 4 bins. So by putting 5 balls in each basket, we could represent it with these stars and bars. Or if I put 14 balls in the first basket and 6 in the second basket, there's how we could represent that with stars and bars. So what we see is that the different ways to put the balls away matches the different ways that we could insert the 3 bars between the stars. Thus, of 23 total symbols, how many ways could I pick 3 of those symbols to be bars? So the answer to this question is 23 choose 3, which gives you 1,771. Now let's move on to a related problem that's a little harder. How many ways are there to put the balls back if each bin has to have at least 3 balls? So here's a picture that satisfies that. Each bin has 5 balls. And here's a picture that doesn't satisfy that. And those 2 bins at the end don't have at least 3 balls. The trick to this problem is to go ahead and just give each bin 3 balls. Now there are 8 balls left to put away. And maybe we put them away like this. And so here's the corresponding stars and bars chart. And what we see is that we've got 8 stars and 3 bars, so 11 symbols. So the answer to this question is 11 choose 3, which is 165. Let's look at the hardest version of this problem. How many ways are there to put the balls away if each bin must have no more than 6 balls? So here's a picture that satisfies that requirement. And here's a picture that doesn't. See, that first bin has way more than 6 balls. And this one turns out to be a little bit more difficult than the previous 2. And so we're going to need another math concept to help us out here. First, let's look at the complement rule. The number of ways to ensure that each bin has at most 6 balls is equal to the total number of ways to put the balls away with no restrictions, minus the number of ways that some bin could have at least 7 balls. And we already know the total number of ways to put the balls away is 1,771, so it remains to count this red, and we're going to use what's called the advanced principle of inclusion-exclusion to do that. So let's choose one bin initially to get 7 balls. Well, there's 4 choices for which bin could get 7 balls. So we're going to take 4 times something. And just to help us visualize, let's say we put 7 balls in the first bin. Now, that leaves 13 balls to put away. Here's the stars and bars chart to represent putting those other balls away. 13 stars, 3 bars, that's 16 total objects. So we should do 16 choose 3 to get 560 here. And that's just how many different ways you could put the 13 balls away if you filled the first bin with 7 balls. So we should take 4 times 560 to get 2,240. Wait a minute, that's way more than the total, 1,771. So clearly we've overcounted. And for example, if you filled the last bin with 7 balls first, you could still arrive at this configuration to the left. So it looks like maybe we've double counted the number of ways that 2 bins could each have 7 balls. So to fix this, let's just subtract that from 2,240. Let's choose 2 of the bins to initially get 7 balls. There are 6 ways to pick 2 of these 4 bins. So in my picture, say I picked the outer 2 bins, well then you've got 6 balls to put away. We could represent that with our stars and bars chart like this. And the point here is that there are 6 stars, 3 bars, so 9 total objects. So there should be 84 ways to put the remaining 6 balls away for this picture. So there's 84 ways for each of the 6 ways we could put 7 balls in 2 bins, so take 6 times 84, and you get 504 here. Now wait a minute, it's possible we've overcounted again. 504 looks like it would double count any time that 3 bins might get 7 balls. So maybe we need to subtract that number from 504, but 3 bins getting 7 balls means we got 21, and we don't, so we're all done. Thus, how many ways some bin could have 7 balls, at least 7 balls, is 2,240 minus 504, which is 1,736. And that's the number that we're going to subtract from 1,771, and we see that the number of ways to ensure each bin has at most 6 balls is 35. Thanks for watching. If you enjoyed this, subscribe.